At 481 feet tall, the Great Pyramid was the tallest building in the world for nearly 4,000 years. Its cardinal alignment is so precise that the base deviates by less than an inch, a level of accuracy that has, for decades, led people to look for explanations outside of human capability, crediting everything from ancient aliens to lost magical arts. The physical requirements of the site, however, demand a grounded explanation. The structure is built from roughly 2.3 million stone blocks. While most are limestone, the internal chambers are reinforced with solid pink granite beams, some weighing up to 50 tons. Historical records suggest a 20-year window for completion, coinciding with the reign of Pharaoh Khufu. To hit that deadline, the construction crews had to quarry, move, and perfectly set one block every 2 minutes, 24 hours a day for 20 years. Identifying how a Bronze Age society met this demand requires looking past the mythology and toward the specific archaeological record, from the translated logs of site supervisors to subatomic scans of the pyramid's core. These records suggest that the pyramid's scale is a result of calculated industrial logistics, where every architectural feature served a specific purpose in a massive, coordinated effort. The pervasive image of 100,000 slaves toiling under whips is a Hollywood invention. The labor force was not a mass of captives, but a highly structured organization of roughly 25,000 skilled citizens. These workers lived in a dedicated village and were provided with a steady diet of beef, sheep, and beer. However, the physical toll was undeniable. Skeletal analysis of the workers reveals a high prevalence of arthritis and compressed lower vertebrae, the direct result of moving massive weight over a lifetime of labor. The first hurdle was horizontal transport. Dragging a multi-ton sledge across dry, hot desert sand generates immense friction, making it nearly impossible to maintain a fast pace. The solution was surprisingly simple. Workers poured a small amount of water on the sand directly in front of the sledge's wooden runners. This created a thin layer of moisture that allowed the sledges to glide, cutting the required pulling force by half. For stones sourced from distant quarries, the Egyptians utilized a now extinct branch of the Nile that flowed right to the Giza Plateau. The Diary of Merer, a logbook from an ancient official, details the use of cargo boats and a 200-meter L-shaped jetty to deliver these materials directly to the construction site. This supply chain effectively turned the local environment into a delivery system, moving millions of tons of stone from the riverbank to the base of the structure. Once the stones reached the plateau, the challenge shifted to vertical height. The traditional explanation is the use of a single massive external ramp leading to the summit. Physics limits the incline of such a ramp. For a team to move a 2-ton block, the slope cannot exceed 8%. To reach the 481-foot peak at that angle, a ramp would have to be over a kilometer long, requiring more stone and fill than the pyramid itself. However, the geometry of a pyramid concentrates most of its mass at the bottom. The lower third of the structure contains 80% of all the stone used. A shorter external ramp could feasibly handle this initial bulk. But as the structure narrowed and the height increased, the builders needed a more sophisticated mechanical approach to finish the remaining 20% of the monument. One leading theory suggests that after completing the base, workers began building from the inside out. They may have used an internal ramp, a corkscrew path built just behind the outer casing, allowing teams to haul blocks to the top without an external structure. This interior focus sheds new light on the Grand Gallery. This 45-meter-long hallway is uniquely steep and narrow, featuring strange stone benches that run the entire length of the floor. Those benches likely functioned as tracks for a counterweight system. By loading heavy trolley cars and sliding them down the gallery's steep incline, the builders could generate enough force to hoist the 50-ton granite beams into the upper chambers using a series of pulleys and ropes. In 2017, scientists used muon radiography, a process that tracks subatomic particles from space, to peer into the pyramid's core. This allowed them to map the interior density without disturbing the stone. The scans confirmed a massive, previously unknown void directly above the Grand Gallery. While its purpose is debated, its location suggests it was a critical part of the internal infrastructure, possibly functioning as a stress relief chamber or part of the counterweight system. Other research from 2024 proposes that subterranean shafts could have acted as a hydraulic lift, using water pressure to float stones up through a central axis as the structure rose. When these features, the internal paths, the counterweight gallery, and the potential water lifts, are viewed as a single, interconnected system, the Great Pyramid begins to look less like a pile of rocks and more like a complex mechanical assembly. Although we lack the original papyrus plans, the physical evidence of ramps, trolleys, and hydraulic networks suggests a sophisticated understanding of mechanical engineering. Attributing this work to supernatural forces or extraterrestrial help ignores the actual evidence of human labor and the biological toll it took on the people of the Fourth Dynasty. The monument is the result of thousands of people working in coordination, utilizing Bronze Age mathematics to solve a mega project that would challenge modern contractors even today. Each block represents a specific human action: a stone cut, a sledge pulled over wet sand, and a beam hoisted by hand. The Great Pyramid is not an unexplainable anomaly. It is the enduring physical proof of human resilience and the sheer power of collective engineering.